Hi everyone. Today I'm going to give an update on the milliohm meter I made a few years ago. Made some improvements to it, which I will describe in this video. Talk about some measurements I made with some standard resistors, and go into some design details which I had probably not given earlier. That might be useful to those who are trying to make something similar. So starting with this overview, this video is going to be mostly some slides and some data, no lab demos and so on, since you have seen this before. So I'm going to talk about the characterization, which is basically the effects of inaccuracies that I've seen over the few years that I've been using this for various measurements. So the first important thing I noticed was the effects of temperature, and that is basically results in gain errors, and mostly has to do with the reference voltage change and also the change in the resistance of the main current setting resistor, which I will show later. There are also residual offsets from the uh, input offset of the instrumentation amplifier plus the offset of the offset compensation loop itself, and so I will go into that a little bit. The third thing is the repeatability, which is also kind of important when you do very low valued resistances where probe positioning makes a difference, mechanical and electrical related uh, effects, perhaps due to the dissimilar metals or various contact related stuff, again for low resistance makes a difference. And there's also the effect of aging of components, warm up time where your meter may be warming up or your instrument itself is warming up. So all these have to be taken into account when you're doing kind of precision measurements in these very low value resistance cases. And of course, absolute accuracy is related to all of the above three things I just mentioned. So we will look at that and compare with a standard resistor in terms of characterization. So improvements I made have to do with initial design was to use 4 wires, but to combine them two into a clip which has the voltage and current sense on the same clip with a very short distance between them, which is typically used in a lot of setups. But I decided to put in 4 banana jacks, so I have flexibility in doing either the 4 separate clips or 2 clips with the 4 wires. So essentially separating out the current injection and the voltage measurements. The second is the improved housing, which is slightly more robust. It's completely sealed with a nice looking cover and so on. The third is replacement of the instrumentation amplifier, which I didn't think was going to be a huge issue, but people have said that you should use a very good instrumentation amplifier, low offset and so on. But the loop itself does compensate for most of the offsets, and the variations are gain error can be calibrated out at a certain temperature. And the last thing is I added a small fan to pull in outside air, which is at ambient temperature into the box, which helps to maintain a certain temperature instead of too much heating that goes on within the box, because there is some power consumption from the power supplies and resistors and so on inside this box. So we'll look at that also. So that's the overview. Let's get into this a little more detail next. So before going into a lot of detail about the measurements, I want to go over a quick review of the block diagram to those who may not be familiar. On the left side, you have the 3 blocks which set the currents for the R dot, which is a device under test. The device under test has the 4 terminals that I mentioned, the 2 driving terminals for the current and the 2 sense terminals for the voltage. And those 2 sense voltages are sensed by the instrumentation amplifier. The switches around inside device are for offset cancellation, so I'll describe that in a bit. The top we have the current mirror, which multiplies, which essentially sets the current through the RI set, which is in this case around 12 ohms or 13 ohms. The current absolute current is not important as long as it's low drift for the resistor. And the 1.25 volt reference is a fairly good one in my case. It's not a extremely high precision band gap, but it's good enough for this, where it maintains I think around 0.01% or so accuracy. So that sets the current essentially, and the variation in that current affects the gain of this device, and so that's the temperature drift we are talking about. The current mirror itself should not have any inaccuracies. Again, that can be calibrated out, and hopefully that doesn't, it's got large enough devices that it matches very well inside. So there's other blocks like the clocking, which which provides the pulses for the offset cancellation loop, which is a very simple 555 based design that produces a small short negative going pulse during reset or offset cancellation. And there's a power supply which uses an external unregulated supply to produce +5, +9, -9 roughly. That the +9, -9 essentially sets the maximum output range of the V out. So in my case it's around 8.5 volts if I use a 9 volt supply, and if you use a 12 volt supply you should get slightly higher voltages close to 9 volts. The instrumentation amplifier right now, the original design had LM324, but in this design I have tried other amplifiers and I will mention those later. And the offset compensation amplifier is a self chopper stabilized amplifier which has fairly good performance, fairly low offsets, and so that's required because that's final offset that shows up at the output. It is an offset compensation capacitor C off, which holds the charge while the loop is not compensating anything. So S2, three switches, S1A and S2B and S3B are the three switches we have. The B indicates they are in the same phase, whereas A is in the opposite phase, that is inverted polarity of the clock. So during offset cancellation, S2B and S3B are momentarily shorted for a very short brief period of time, and most of the time it's S3A, S1A is connected to the instrumentation amplifier, which reads or is continuously sampling the input for the resistor. So this is basically the overall description of the block diagram for this milliohm meter. We can look at now the temperature effects that can happen and come up with some strategies to improve that. Essentially, these most important devices are the RI set, which is the resistance I talked about on the left side, and the 1.25 volt reference that is used. Everything else are second order effects as far as accuracy is concerned. So let's look at the effects of temperature first. So any change in the 1.25 volt reference will change the current, as I mentioned earlier, because that sets the current in the overall R dot, and so that results in a direct gain error or slope change, which is the voltage that's coming out of the instrumentation amplifier. So that is kind of important as far as accuracy is concerned. So using a low drift reference will mostly get rid of this problem. The LT1634 that I've been using is 10 ppm, which is more than sufficient for this application. The second device that has impact on the accuracy, and this is probably the most important, is the RI-set temperature drift variation due to heating, self-heating. Is the same effect as the change in voltage because it sets the current in the R dot, which affects the gain. And so this is the main thing I needed to actually work on, and actually I haven't still replaced that resistor, but I kind of understand where the biggest source is now, so I probably will do that in my next iteration of this design. So right now I'm using a very small SMD resistor, which I think is not a good idea, but it's still, if you look at the result, it's not that bad overall, even because of the other things I've done. So even standard resistors, which you may get which very high accuracy like 0.1%, will have temperature drift, and that's a separate top effect compared to accuracy. We are not too concerned about accuracy because we do calibrate that out, but we don't want variation in that due to temperature. So even if you put a real, it's impossible to of course put in a real standard resistor which has very low temperature drift like that you use for measurements and for calibration. So we need to compromise by using a low drift tiny resistor that can fit into this box. So that's the thing we need to do as far as getting the accuracy as much as possible without affecting the performance of this instrument. So I'll probably will do that in the next change. I need to just order the right device and then make sure it fits into the existing area that I have for this particular the PCB that I have. So the next important thing to talk about is residual offsets. So we have offsets coming from the instrumentation amplifier, which is cancelled by the offset loop. And usually that's going to be a static offset. Of course, every time you power on the chip is likely to be different slightly, but essentially it has a certain offset, either positive or negative, and that gets multiplied up by the 10x by the instrumentation amplifier, and that is compensated for by the offset cancellation loop. So the gain is 10 here, and the biggest source of offset is the first gain stage, which is the 10, and there's a buffer after that of a gain of 1. So the main offset is really in the first stage. So if there were no offset compensation, the input offset would translate into a 10x in terms of milliohms or ohms, whatever the unit you're using. So if you have 1 millivolt, you have a 10 millivolt of X out change at the output, which results in a 10 milliohm error. So using a low offset amplifier will effectively reduce the work the offset loop has to do, and basically divided down by the gain of that loop. So better to have as small an offset as possible, but you don't have to go crazy about it. So if you have a 60 dB cancellation, then a 1 millivolt gets translated to effectively gets divided down by 1000 and then multiplied by 10 again. So you get a 10 microvolt of offset, which is 10 milliohms in this particular case. The second source of offset is the offset compensation amplifier itself. Even though it's chopper stabilized, it will have some variation, some residual offset in the microvolts. So that is going to be roughly in the ballpark of the instrumentation amplifier divided by the loop gain. So what typically you want to do is to keep both these offsets in the same area, same level of value. So you basically have a optimized loop for that. You don't want to make one very small, because that doesn't buy you anything really. So in this design I have an LT1049, which is the chopper stabilized amplifier, and it has a maximum of 10 microvolt with a very low temperature coefficient of 0.1 microvolts per degree Celsius. There's also an LT1050, which I had used in the past. That's a 5 microvolt offset and slightly better performance than the 1049. Right now I have a 1049 in this setup. Since I use a single point calibration, that's how the entire instrument was designed. I didn't want to have to deal with calibration at 2 points. I said, okay, let me calibrate at one known point, and then because of the offset cancellation loop, it should theoretically be zero at zero resistance, but of course that's not going to be true. So that sets a limit. Any residual offset limits the minimum value of resistance that you can actually measure. A 2-point calibration, I think, would drastically change the design, and I haven't looked into that in this particular setup. I haven't even studied it. It's possible, I bet, but most of the simpler designs that you see on the internet are 2-point calibration, where I think they get rid of they set the slope at all 2 points, which helps to essentially improve the accuracy within that range. I think once you go to the sub-milliohm region, the effect of other effects like mechanical effects and positioning and things like that play much more of a role than just the electronic effects that I'm seeing over here. So I think we'll have to look at that next in terms of overall accuracy. So this brings us to the topic of repeatability. So we have looked at how to improve the design from electrical point of view, but repeatability essentially for these type of low value resistances is kind of probably more important when you get into the sub-milliohm realm of absolute measurements. Originally this was designed to measure absolute resistances from around a few milliohms to 10 ohms. So at the low end is where I have most of the problems in terms of meeting the accuracy because of the residual offset and any gain errors that are left over. So in my experiments, the probe positioning, the quality of the probes itself, especially if you're using this tube clip approach where you have this I drive and the V sense at the same location, but there is some distances between them and there is some you don't know how the current actually flows between them and how well the contacts are made. So those can impact the repeatability quite a bit. So I have options to use 4 wires, separate wires. So I think that will dominate one of the what is kind of one of the sources of error in terms of repeatability. The second thing is, of course, or the third thing is the leads, the positioning, where you position them. A few millimeters can make a difference in hundreds of microvolts even on a even fairly thick wire on a component, for example. So if you want to really measure down to milliohms absolute, you have to make sure you're positioning at the right location, you have a good grip, clean contacts, clean wiring, everything that you're actually sensing. And some of the smaller components, it may be hard to get a good feel for where exactly to probe it. So there are some challenges. On the other hand, if you have a large shunt resistor, but those shunts typically have large terminals, it's probably easier to measure them. But at the same time, you're talking about total resistances of hundreds of microohms. So that's also a challenging measurement. One way to improve is to do averaging, so that gets rid of some of the noise in the system, and that's what I've been doing to get to when I'm doing the calibration part of it using a standard resistor. I average over hundreds of readings if possible. One downside to this design, which is not related to repeatability, but it's also a factor that you have to consider, is that this is a sample system. So the voltage that's coming out of the system is not constant over the period of the clocking. So as soon as the zero offset is done, that's when the maximum offset, the actual offset is held on the C off capacitor, and it'll slowly drift down depending on leakage and other effects there. So if you want to get a true measurement, you have to sample this right at the point where reset or zero cancellation is completed, and then sample it for a short time and then do it again repeatedly. So that's the best way to get the accuracy and repeatability you want. I think it's possible to improve that in the next design by using a sample and hold system. So I need to improve the clocking, maybe add non-overlapping clocks and so on, but that's quite a bit of a difference in the design. But that's definitely possible, so you avoid this issue of sampling at the output, which is needed in this particular design. So let's quickly go through the improvements I made. So the first one, as I mentioned, is this for using going for the 4 coaxial cables to having banana jacks, 4 banana jacks on the outside. So it gives you more flexibility in terms of how you want to sample or connect to the DUT. So now I have 4 separate wires, or the option to connect a 2 probe clip as well. So I have that option now. I've also printed a bigger 3D printed housing for this milliohm meter. It's more robust, it's completely sealed, and has room for some expansion if I want to add some additional components if I have to. I replaced the original LM324 op-amps with other chips to check the impact of accuracy. While the LM324 has got a maximum of around 7 millivolts at 25 Celsius, and it's over actually 10 millivolts over larger temperature ranges. So this is quite large. So you might see something like 100 millivolts at the output without any compensation. The OP007 has much better offsets, and so I have some results from that. For the offset amplifier, the LT1050, as I mentioned, has 5 microvolts. The 1049 has 10 microvolts. So these are pretty good, and either one should be okay to use, and currently have the LT1050. And then we have the important improvement that I made, which is to add a fan to keep some of the critical temperature inside the device fairly constant, close to ambient as much as possible. So the fan blows in air from the right side of the box where there's not much heating going on, and so it pulls in a cooler air and pulls it over the resistor and some of the reference areas, so it kind of cools that a little bit. So the temperature rise is not as much as it used to be before. So that I think definitely helped to keep the overall accuracy, improve the overall accuracy. But if there's a change in the ambient temperature, of course you're going to have some changes, and that's what I will show in my measurements. So here's a quick look at the pictures that I have of this new box. You can see on the top left is a completely sealed unit with a cover and the 4 terminals coming out. You can see some holes on the right side for the fan to draw the air in from outside. The next picture on the right shows it open with the front a little bit more visible. There's an LED which blinks every time there's a sample going on, the yellow LED. And then the bottom left picture, you see some of the insides. There's some room left, but it's still quite tight, but I think definitely a better box than what I had before. On the left side, you see the fan that pulls in air from the right side, and the airflow is from right to left in this picture. And the last picture, the bottom right, is the back side, which shows the trigger output for the, in case you want to sample the output at the right at the 0 offset location on the timing waveform, and V out goes to the meter, it's the analog output, and the power supply jack on the rightmost location there. Okay, so it's time to get into the measurements. I fabricated a crude Peltier based heating cooling system to raise and cool the temperature of the entire box as well as the components if I needed to, the RDUT for example. I did it over a fairly small range. I couldn't really get too much of a temperature variation out of this Peltier system, but it was, since it's heating and cooling a fairly large area, volume actually. So I did that, and I had 2 standard resistors, a 1 ohm and a 10 milliohm, and with these I calibrated at 1 ohm, a single point measurement, and basically I'm assuming of course the offset is 0, which is not true. And then I evaluated the results at 10 milliohms. And the future I plan to calibrate this at 10 milliohm because that's where I should really be trying to optimize this design. So right now let's assume that all the results are actually based on this 1 ohm calibration. Okay, so this is the measurement of the 1 ohm standard. So this is fairly detailed results over here, and we have 2 cases, one where I have the 1 ohm standard resistor and the meter in a temperature control environment. And the leftmost column is your temperature in Celsius from 19 to 27 degrees Celsius. Then you have the R min, R max, R average, which coming out of the meter, the HP 34401A, and then the number of readings I took for at each of these temperatures, and then have a error calculated based on a 25 degrees Celsius being a 0 error. So you can note that my actual calibration is off by around 2 milliohms for the 1 ohm resistor, but that's okay. I'm trying to look at more relative effects. Gain error can be changed slightly later. And then on the rightmost columns you can see the TCR of R plus the meter, which is in this case minus 44.5 ppm, and the delta R percentage shows the variation of the resistor from the 25 degrees case. So next, the bottom set of columns is, sorry, bottom set of rows of data is for the 1 ohm standard. Basically only the meter is kept in the temperature control environment, so this is checking the effect of temperature on the meter, not on the resistor. So the resistor is at ambient temperature at around 25 Celsius, so this tells you how much the meter itself is moving around with respect to temperature. So the key takeaways is that if I assume that the 1 ohm resistor is on target, which I think it should be, it's a very accurate 1 ohm plus minus 0.01%, then I can calibrate this meter against at 1 ohm. I just need to account for that 2 milliohm variation, which I can calibrate out in the future. So the total combined tempo for the meter and the resistors minus 45 ppm, the topmost set of readings, and then by keeping the resistor at 25, and I can extract the effect of temperature on the meter itself by using the formula below, which is the statistical effect of taking the sum of squares and square root of that. So we have the temperature coefficient of the meter to be around 37 ppm or so, minus 37 ppm. So I think that's pretty good, considering that the temperature varied almost 8 degrees over this thing, and typically in a room temperature environment this variation is probably reasonable, maybe a little bit higher or lower than this, but even if I didn't do anything, I think this will be fairly easy to live with. I mean, I could even compensate for this with if I put in a formula for the slope of this particular equation for the error. So next I took the 10 milliohm resistor and I measured that with the calibration done at 1 ohm. So this is kind of to confirm how much the slope error is there, or even offsets that may be present in the meter. So in this particular case you can see that the standard resistor I assume is also exactly 10 milliohms, and the R max is 10.41474 milliohms, and then the R min is 10.155 roughly milliohms. So the average came out to be 10.2793 milliohms or so. So over 256 readings, the R error is about 2.8%, and the estimated sigma for this is around 0.05 milliohms, or roughly 50 microvolts or 50 micro ohms. So calibrating the meter at 10 milliohm will most likely I can get out of this 2.8% of systematic error, but when we'll still need to accept a higher because of this. Of course, it's calibrated at 10 milliohm. At 1 ohm, it's going to be worse, but I think that's okay because this is really supposed to be targeted for milliohm measurements. So I would like to make sure I target this calibration also at a low temperature, low resistance value. So I think that's the next step to do this. I do have a better temperature setup that I'm building right now, and I'll probably describe that in a future video, and that will allow me to go over a slightly larger range with more accurate temperature control. So I think this is fairly decent results, 3% at 10 milliohm. I think I could maybe bring that down to close to zero, then I probably get better results at even lower milliohm values, but accept slightly higher errors at higher values. But then other meters which are designed to operate at higher resistance are probably more accurate and designed for that, so I am not too concerned about that. This specific application requires the milliohm kind of accuracy, so that's where this meter will shine, I think. So the last measurement, and I did this for fun, is to actually take a regular resistor that is just lying around. I have a 2 ohm high voltage resistor. I thought I should measure that and see what it looks like as far as its temperature variations are concerned. And you can see it's the curves below which kind of highlight that. So the blue curve at the bottom in the graph is actually just the meter temperature variation. So I kept the 2 ohm resistor at 25 Celsius and changed the meter temperature over the same range. There's slight difference from the previous measurement. You can see is slightly positive. I'm not exactly sure why, but I think it could be my measurement temperature setting may not be as good because I don't have a very good controlled environment for that. But it's still roughly in the less than 50 ppm or so, which I think is acceptable. And overall, I think the meter should be doing fine over this type of temperature range. But you can see that the the orange curve is really the variation of the resistor itself, because both the resistor and the meter are at that temperature in this particular set of experiment, and that's about like 360 or so ppm, which is fairly large, I think. So you can actually do this kind of measurement, and um, in this particular setup, if you have a good sampling system with this HP4 or any kind of a digital meter which has sampling on it, I can do some accurate measurements on various types of resistors over temperature, and even put in a graph perhaps to for different types of resistors you can compensate out the value and make sure you're getting the right reading at room temperature, for example. One thing I forgot to give some data on was on the replacement of the LM324 with the OP007. I think I should do that right now, although I don't have a slide for that. When I did the LM324, I could measure the actual offset that was being held on the offset capacitor, and that was 23.5 millivolts in my setup. So that roughly translates to 2.35 millivolts of input offset. When I did replace the it's not OP07, it's OP400. So that OP400 had a residual offset at 0.5 to 1 millivolt or so. That's fairly small. So you can see it's almost like 20 times to 30 times smaller than the input offset of the standard LM324 op amp, which is a very generic op amp. But the surprising thing was that output variation for the 1 ohm standard for the LM324 was about 760 microvolt change for over at a given temperature, for example, over a fairly large number of readings. So that's 786 microvolt of change on a 1 ohm resistor, whereas with the OP400 that same variation I saw was around 440 microvolts. So it's not even half of the actual offset seen by the LM324. So the op amp itself is not that critical. The offset loop takes care of most of it, and although you can use a better op amp, you're not going to gain that much. But I think when you're going into very low resistance measurement, this becomes critical, that you want to use a good op amp for both the offset cancellation op amp as well as for the instrumentation amplifier to basically reduce all these errors. And other thing I can tell you is that when I try to measure a 750 micro ohm shunt resistor, my resistances readings were quite off. I mean, maybe 10-20%, and it wasn't very stable. So that's something I need to improve, and maybe the setup needs some improvement. It could be also power supply noise and other kinds of noise effects now showing up, the offsets themselves, the gain error. Maybe a calibration at 10 milliohm or even 1 milliohm might be necessary for that kind of measurement. So that's this as far as measurements are concerned. So let's summarize next. So some questions have come up from viewers and others who have looked at my meter, and so I want to try and summarize and add some additional comments over here. So as far as the op amp itself, for the low input offset, if you use a low input offset op amp, I think that is probably the most critical thing. The input current, if it's the typical modern op amps, which is few nanoamps, I don't think that makes much of a difference. So I tried a TL084 and other type FET input op amps, and they didn't really make a significant difference in terms of the measurement results. I think using a low offset does help a little bit, as I mentioned in my last slide. The best op amps will be the ones that have the low offset rather than any other parameter that you want to worry about. Secondly, the CMOS switches I used were a little bit expensive, but I think they were worth it. They had the normally open, normally closed outputs, which meant I didn't have to invert the clocks coming out of the clock generator, which would have been a simple thing to do, of course. But at the time I also was thinking about using that switch in the actual R dot path to extend the range by changing the R iset resistor than using a switch. But I think I didn't do that eventually. So for that particular kind of application where you want to have a fairly large current going through a switch, you want to have low resistance there, and even that resistance will vary. So I didn't pursue that option actually, although I could keep one of the branches of the R iset continuous without a switch on it, so that would probably help. But at a higher resistance, you don't have to worry that much about the actual resistance of that switch. So I'm also particularly partial to CMOS technology, so I kind of use that MAX 4660E CMOS switch. The frequency of the clock is not that important as long as it's reasonably stable. It doesn't. The main thing is you want to be able to set the pulse width, and you also want to be able to change the frequency a little bit. So there are some easy adjustments one can do there. You just need to make sure that your op amps, the offset amplifier, has enough time to settle out any variations. And if it's like several hundred milliseconds, that's enough. And this is a fairly low speed system, so I think that's easy to do that. Of course, you have to sample the whole thing, so that's make sure you sample at the right location to get the best accuracy. So last thing I did as far as measurements, I did have this HP34401A, which has a sample trigger input, which is useful in this thing, because if you don't use that, you're going to see the resistance vary over the measurement as it progresses along. So you want to sample it and hold it and then capture it and then put it into a statistical, basically do some math on it. So that's what I did. In many cases I sampled hundreds of points and that averaged them. It doesn't have the statistical function for sigma, but I think you can estimate that based on the number of samples you have, and if you assume normal distribution, I think you can come up with some reasonable accuracy kind of estimates for sigma. So that's what I did. So this has been a long video. I hope this is useful, and hopefully next I would like to probably show the temperature setup that I have, which I'm building right now, and talk about that in the next video. Thanks for watching. See you next time.